Hello again. Welcome back. This is video lecture 11.4, and we're going to start our discussion with chapter 11, section 6, Newton's second law in angular form. We already have an angular or rotational version of Newton's second law, so what does this mean? This means there's going to be a new way to write that. Okay, so Newton's second law in angular or rotational form. Well, let's just kind of, for the moment, argue by analogy. When we studied translational motion along a line, we started, the first way we ever saw Newton was this way. F net equals m times a. But then we learned a little bit later that using the concept of linear momentum of a particle of mass m and velocity v, right there, you could write Newton's second law in the form, and that should say F net, sorry about that, F net equals dp dt, the derivative of the linear momentum with respect to time, or the rate of change of the linear momentum. And we used both versions of Newton's second law, whichever was most convenient in a given situation. Then in chapter 10, where we had a rigid body rotating about a fixed axis of rotation, so we had rotational motion, we came up with a rotational version of Newton's second law. And that's right here. The net torque about the given axis of rotation is equal to the rotational inertia about the axis of rotation times the angular acceleration, alpha. And I've written that with vector symbols. And now we're going to come up with one more expression, another way to write the rotational version of Newton's second law. And it's analogous to the second translational version of Newton's second law. F net equals dp dt. What is that going to become when you look at the rotational version? Net force becomes net torque. And rate of change of linear momentum becomes rate of change of angular momentum. And that's the newest form of Newton's second law. For a particle, the net torque on the particle equals the rate of change of that particle's angular momentum. Where I will remind you that we have now learned how to calculate angular momentum for a particle. It's the vector product R cross P. Heads up, in the rotational version, the torque and the rotational inertia and the angular momentum all must be calculated about the same chosen point for consistency's sake. If you don't do it that way, you'll get answers that are nonsense. Okay, so now I just want to show you a picture and give you a sense of where that latest result comes from, because it might seem a bit arcane or mysterious, and I don't mean for it to be. I'm talking about tau net equals dl dt. So let's take a very specific scenario, a kind of a picture I've drawn now multiple times. It'll have to be a 3D picture, so let me try to represent a three-dimensional coordinate system on a two-dimensional surface. We have an xy plane that's horizontal, and then vertically up is a z-axis. There's our origin O. And let's say there's a moment in time. Let's call that time 0. And at that moment, our particle is located somewhere in the xy plane. So its position vector, r, would point from O out to where the particle is at that moment. That would be the r. Okay, now let's say that at that moment, that snapshot in time, the particle was moving. It has a velocity, v arrow. Therefore, it has a linear momentum, p arrow, in the same direction as v arrow. And let's say, just for the sake of having something explicit to think about, that velocity and therefore linear momentum excuse me, is in the negative y direction, or parallel to the negative y axis. So the particle is moving to our left in the xy plane at this moment in time. Let's use the right-hand rule and get the direction of its angular momentum, this particle's angular momentum L at this moment. I want you to try that for yourself. You need the right-hand rule. You can see the r and the p. Those are the two vectors you need. What's the direction of L, about point O, for the particle at this time? Pause the video so that you can do the right-hand rule slowly and carefully, and then when you're ready, come back. Okay, did you say that at this moment, the particle's angular momentum points in the negative z direction, vertically down from the xy plane? And that's what I'm trying to draw there with that green arrow labeled L. That came from the right-hand rule. Slide the r out so that its tail is at the particle, so that r and p have a common tail. And then I recommend using the two-pen method. Let me get my two pens here. I'll use a blue pen for R and a red pen for P, and Vinny will help. And so R is kind of like so, and P is like so, and I slide them so that they have a common tail. Good job, Vin. So R and P, and then I have to hold them so that I can see them. And I have to reach in with the fingers of my right hand, with my fingers along R, with my palm facing P, and push R on top of P and see which way my thumb points, and my thumb points down. That's the negative z direction, vertically down from the xy plane. That's why my green arrow labeled L points down. That angular momentum arises from the fact that the r vector for the particle is rotating clockwise about O at this moment. All right, now at this moment, something else is happening. There's a force pulling on the particle. Let's say the force is also in the xy plane, but maybe is that way. Okay? So that's also what's happening. So that's the whole picture now. Particle, it's got a certain linear momentum, a certain position vector, and there's a force acting on it, all at this moment in time. All right, I'm going to start with the expression for the angular momentum of that particle, L equals R cross P. I'm going to next write out what P is, symbolically, m times v. Okay, so that's the expression for the angular momentum. I claim that with this picture that you see right now, not only does the particle have a certain angular momentum about O, but now because of the force, there's a torque on the particle about O. Okay? All right. So the claim is that that torque is going to cause the angular momentum of the particle to change. I want to show you how that is going to come out. I started with the expression for L there. Now all I'm going to do is take the time derivative of both sides, dl dt. Got to do the same operation to both sides. So I'm going to do that operation. Whoops, sorry, didn't mean to do that. I want blue. D by dt of this quantity on the right-hand side. R cross mv. Cross is a form of multiplication for vectors. So what I'm really doing on the right is taking the derivative of a product of vectors. Yes, the derivative of a product, we have to use the product rule. We'll have to take the derivative of the first vector crossed into the second vector, plus the first vector crossed into the derivative of the second vector. That's the product rule. So let's see what we get when we do that. Derivative of the first vector, dr dt, crossed into the second vector, cross mv, plus first vector, r, crossed into the derivative of the second vector. The m in that expression is a multiplicative constant, so you can write that as m times dv dt. Okay? Yes, that's the product rule. You may need to pause the video and think about that a little bit, but that's what that looks like when you've got a product of vectors. Now we just need to remember some things we've already learned. By definition, the derivative of the position vector with respect to time is the velocity vector, v, arrow. And by definition, the derivative of the velocity vector with respect to time is the acceleration vector, a, arrow. So now let's write out dl dt again. Looks like I have v cross m times v plus r cross m times a. Rather interesting looking. Now I want you to look at this first cross product. V cross mv. M is a, look at this part here first, the m times v. M is a positive scalar. So when I multiply v arrow by m, I get a new vector. It'll have a different magnitude than v alone, but it'll be in the same direction as v. M times v is a vector that's in the same direction as v. So I'm taking a vector in the same direction as v, and I'm crossing it into v. Where's all this going? The two vectors I'm crossing in this first case are parallel to each other. They're in the same direction. So when I calculate the magnitude of that cross product, I have to take the sine of phi. Phi is the angle between the two vectors, but the vectors are in the same direction. So what's phi? What's that angle? It's 0. What's the sine of 0? 0. This whole first cross product vanishes. Wow, that helps a lot. Got to understand vector algebra. Then vectors are your friend. So what are we left with? dl dt equals r cross ma. Well, that looks pretty simple. Now, what are we going to do with the ma? Doesn't that look familiar? That's a particle. What can I replace ma with? What is that equivalent to? Did you say F net? That would be the good answer. So, dl dt equals r cross F net, because technically it's F net. Now, in my application, F net is just that one F you see in my drawing, right? But wait a minute, what's r cross F? Did you say torque? Tau? So that's what I'm going to replace on the right side. So what I have just done is derive that new expression for that specific situation I drew in my picture, of course. That the torque is equal to the rate of change of the angular momentum. Torque causes angular momentum to change. And the torque is equal to the rate of change of the angular momentum. So now here's the next thing I want you to do. For this picture, I want you to use the right-hand rule and tell me the direction of the torque, tau, on the particle. Pause the video. Please do the right-hand rule carefully for practice. Get an answer, and when you're ready, come back. All right, did you say that the torque on the particle is vertically upward, tau arrow in the plus z direction? Did you slide R and F so that they have a common tail? And then using two pens, holding them in your left hand with R and F with the common tail, take the fingers of your right hand with the fingers along R and the palm facing F and push R on top of F. Your thumb will point up. So the torque vector on our particle in this case is in plus z. But the angular momentum particle in this moment is in negative z. But torque is the rate of change of the angular momentum. So the tau vector is the direction in which the angular momentum is changing. But the angular momentum itself is down. But the direction of its change is up. So what must be happening to L? Well, at least for a while, it's still going to point down, but its magnitude is going to decrease because its rate of change is up. And if that upward torque persists long enough, the magnitude of the downward L will decrease and decrease and decrease until for one moment in time L will be 0. And then L will point up and increase and increase and increase. Because the thing that you got to remember is tau is telling you the direction and the magnitude of the rate of change of L. Not L, but its rate of change. Just like F is telling you the magnitude and direction of the rate of change of P. And this is just the rotational version of that. Tau is telling you the magnitude and direction of the rate of change of L. Okay, let's get right into the practice with that. Practice with Newton's second law in angular form. Okay, in this figure, we have position vector of a particle at a certain instant. Look carefully. The position vector from point O there in the xy plane is that light gray arrow R, because our particle, it may be hard to see it, we'll draw it with a big red dot, is right there. There's our particle. It's at that certain location in the xy plane, origin O. The position vector points from O out to where the particle is at this snapshot in time. And we also have 4 choices for the direction of a force. So all these force vectors have the same magnitude. They just differ in direction. And they're labeled F1, F2, F3, and F4. And they are going to be there to accelerate the particle. And all 4 of these choices for the force are in the xy plane. They're right there, F1, F2, F3, and F4. All of the same magnitude. They differ in direction. They're acting on the particle one at a time. One at a time. Okay, here's the first question for our practice, part A. Rank these 4 force choices, F1, F2, F3, and F4, according to the magnitude of the time rate of change dl dt that they produce in the angular momentum of the particle about point O, greatest to least. All right, let me talk you through how we're going to do A. I'll use some space up here to get started. So let's use our new form of Newton's second law. Net torque, remember only one force is acting at a time, so the net torque will be from the one force that you have, equals the rate of change of the angular momentum. But this problem is only about magnitudes, so we'll go ahead and put absolute values on those. We're just going to be worried about the magnitudes of those quantities. And probably most books would then just write that like this, with no arrows anywhere, because it's just talking about magnitudes. So what we're supposed to rank is that quantity, magnitude of dl dt, for the 4 possible choices of the force. Well, Newton tells me that the magnitude of dl dt is equal to the magnitude of the net torque. So ranking dl dt is equivalent to ranking tau net. So what I'm actually going to rank is the tau net. But that will also be the ranking for dl dt. All right, how am I going to rank the tau net? It's just going to come from one force at a time, and those are magnitudes. I'm going to use this form. I contend that if with a picture, in this case, that's the easiest form for thinking about magnitude of torque. Moment arm times magnitude of force. Remember, all 4 of those forces have the same magnitude. So what I have to do now, I've boiled it all down to ranking the moment arms for the 4 forces, because that's going to help me enable me to rank tau, and that's the same as ranking dl dt, rate of change of angular momentum. So we'll take each force one at a time, and we'll figure out how big its moment arm is. So first for force 1. Now you got to remember how to find moment arm. And I introduced that idea in chapter 10. Let me get rid of some things here. So I'm only focusing on force 1. let me draw its line of action just by extending the F1 arrow. Then I did that with the green dash line. Then, moment arm is perpendicular distance from point O to that line of action. So try to sketch it in here. It's going to be roughly like that. And that I would call R1 perp. It's the moment arm for force 1. You just got to get a sense about how long it is. And the main thing to note is that the length of R1 perp is smaller than the magnitude of R itself. All right. Now let's look at force 2. This one's going to be easy, yes? What's the moment arm for force 2, F2? Did you say 0? Because the line of action of F2 passes right through O. It has no moment arm. The moment arm for force 2 is 0. Similarly, the moment arm for force F4 is 0. Well, that's easy. What about the moment arm for force F3? Well, let's not skip any steps. There's the line of action for F3. Now the moment arm, perpendicular distance from point O to that new line of action. Well, that points right along R itself, doesn't it? So the moment arm for force 3 is the entire magnitude of that R. And that's the biggest moment arm, isn't it? So the ranking of the moment arms is, the biggest is R perp 3. The next biggest is R perp 1. Write it like that. And then the next is R perp 2, which equals also R perp 4, and they both equal 0. So that's the ranking of the moment arms. 3, then 1, then 2 and 4 tie. Therefore, that's the ranking of the torques. Therefore, that's the ranking of the dLdTs. Okay, so the ranking of the dLdTs is, well, let me state that explicitly. Ranking of dLdt. I'm just going to write it like this. 1 is bigger than 3. Oh, I said it backwards. I beg your pardon. 3 is bigger than 1, is bigger than 2 and 4, which are equal to 0. So force 3 will produce the largest dLdt. Force 1 will next produce the next largest, and forces 2 and 4 won't produce any dLdt at all. To say it another way, for force 2 and force 4, the angular momentum of the particle will be constant. All right, now, part B of this, I wish for you to do as class engagement on Blackboard. And here's what part B says. For each force, one at a time, 1 through 4, give the direction of the vector dLdt. I'm not talking about magnitude, I'm talking dLdt vector. What is the direction of dLdt vector? Your possible answer choices are plus x, plus y, plus z, minus z, or 0 if there is no dLdt. Okay, so you put your answers on Blackboard for video lecture 11.4. I'm going to move on to one more idea. This is chapter 11, section 7, angular momentum of a rigid body, a rigid extended body, not a particle. We're now progressing beyond just a particle, because that was the first thing we learned. L equals R cross P is just for a little particle. What if you have an extended body that's rotating? How do you calculate the angular momentum of that? Well, just break that thing up into a whole bunch of particles. Do r cross p for every single particle, and add all those little L vectors to get a total. Now, if you think that sounds daunting, actually it is. It's pretty messy. So I'm going to show you how we're going to simplify the situation a little bit. Okay? So here's a picture. I'm not going to go through all this in detail, and I'm not going to expect you to be able to derive any of this in detail. I just expect you to be able to use the result we're about to get. The picture shows some kind of arbitrarily shaped extended body, some kind of a blob, but rigid. It's not changing shape. Okay? And it is rotating about an axis of rotation. We might as well choose the axis of rotation to be one of our coordinate axes. We'll choose it to be z. Okay? So this blob is rotating about an axis of rotation that we chose to be along z. And we want the total angular momentum of this body. I'm actually going to cheat just a little bit, you'll see. But that's what I want. Well, what we do is we imagine breaking up the body into a whole bunch of little particles. There's one of those particles right there, and the arrow points to it. It's got some mass, delta mi. It's got some position vector from point O, way down there at the origin, r sub I. And it's rotating, and this particle is moving itself in a little circle about the z-axis. And at the time we drew the picture, then, that little particle has some linear momentum, pi, tangent to its circle. And we want to calculate the angular momentum, little li, of just that little piece. So that would be ri cross pi for that little piece right there. It's kind of messy, but I will at least show you in the picture below its direction, the direction of li. Notice the little piece we chose is sitting vertically above the x-axis, and therefore pi is pointing in the plus y direction. So when I do ri cross pi to get li, I have to do the right-hand rule. And li will be perpendicular to the plane of ri and pi, and given by the right-hand rule. And the net result for that li, it's drawn with its tail at the origin, is right above the x-axis by an angle theta, where theta is this same angle there as there. Now here's what we're going to do. Turns out we're only going to need to worry about the component of the angular momentum about or along the axis of rotation, in this case z, the z-axis. So all I really want to keep track of is the z component of li. Li, z component. Well, that would be the magnitude of the whole li times sine theta. And then what I want to do is I want to sum up, add up all those z components of L for the whole thing. Okay? And that's what this idea here is. To get the total angular momentum of the rigid body, we're going to sum the angular momenta of all its constituent particles. Note the notation we're going to use for the total angular momentum of a system of particles, capital L. Just like we used capital P for the total linear momentum of a system of particles. So that's what this says. Capital L is the sum of the little l, but it's vector addition. But all we really want is the z component, the component along the axis of rotation. And when you do all that, the final answer you get, and this sounds really complicated, so it's actually amazing that you get such a simple result. And it's right here. The total angular momentum along the axis of rotation, in this case, capital L sub z, is given by the rotational inertia about the axis of rotation, I sub z, times the angular velocity, omega, from the rotation. And that's the result that we use for the rest of this chapter if we have a rigid body rotating about an axis. Okay? The component of the angular momentum along that axis I'll write it down here bigger so you can see it, is equal to the rotational inertia about that axis times the angular velocity for the rotation about that axis. So a lot of times you'll hear people just say L equals I omega. That's what this means. What they really mean, though, is the component of the total angular momentum along the axis of rotation equals the rotational inertia about the axis of rotation times the angular velocity about that axis. L equals I omega. You can think of that as the rotational version of P equals mv. Okay. So, one more key idea. What's the rotational version of Newton's second law for an extended body? It's right here. Newton's second law for a rotating body non-particle. It looks a lot like tau equals dl dt, but there's some things that have happened along the way. And I'm just going to tell you the result. The symbols, you have to be careful. On the right, I have d capital L dt, the rate of change of the total angular momentum. Total angular momentum of the body. The L part. And so the right is the rate of change of that total angular momentum. And on the left, I have the net torque, but only external torques. Torques from external forces. Turns out internal torques from internal forces in an extended body cannot change that body's angular momentum. So in words, this expression says, a net external torque is required to change a body's angular momentum. And the net external torque equals the rate of change of that body's angular momentum. All right, now, that's where I'm going to do one more thing. I'm going to show you a table where we just relate translational and rotational expressions, because we've had a number of them, and it's kind of handy to remember that there's an analogy between each translational expression and its rotational analog. So I'm going to briefly discuss this table, and then we'll have one more video lecture and class where we will apply the expression I just showed you. And it will give us our third conservation law. All right, so in this table, the first column are some of the important expressions we've studied so far for translational motion, motion along a line. And then for each one, I will have the rotational analog. Of course, force is an important quantity when you're studying translational motion, F arrow. When you're studying rotational motion, the quantity you want to focus on is torque, tau, which is R cross F. For translational motion of a particle, linear momentum is very important. P equals m times v. In the rotational analog, it's angular momentum that's important. L equals R cross P. If you have a whole system of particles undergoing translational motion, the linear momentum of the system is denoted capital P, and that's just the sum of all the little p's for all the particles. What's the rotational version? The angular momentum of a particle system, capital L arrow, and that's obtained by adding all the little angular momentum vectors, little l. Another expression for linear momentum of a particle system. The total linear momentum of a particle system, big P arrow, is equal to the total mass of the system times the velocity of the center of mass. What's the rotational version of that? The angular momentum of a rigid body about a fixed axis, L equals I omega. Next, Newton's second law for a particle system, F net equals d capital P dt. Newton's second law rotational version for a particle system, tau net equals d capital L dt. Finally, conservation law for a closed isolated system. Capital P equals a constant. What's the rotational version? Conservation law for a closed isolated system. Capital L equals a constant. There is our third conservation law. It will be called conservation of angular momentum. But I'm not going to go any more into that now. That's the topic of our last video lecture and class for Chapter 11. So that is all for this video.